It's your lifeline. All right, future aviators, let's talk about something really important. I mean, foundationally important for every single flight you'll ever make. We're diving into the world of drag and something called best glide speed. Now, these terms might sound a bit like engineering homework, but trust me on this one. Understanding them isn't just about passing your check ride. It's about becoming a safer, more efficient, and ultimately, a more confident pilot. Knowing how your airplane fights against the air and how to make the most of its gliding ability can quite literally be a lifesaver. It's about knowing your machine inside and out, especially when things don't go as planned. So buckle up and pay close attention. Think of it this way. Every time your airplane moves through the air, it's in a constant battle. The air, as invisible as it seems, pushes back. This resistance is what we call drag. It's always there trying to slow you down. Now, why should you, a budding pilot, care deeply about this invisible force? Because drag directly impacts your airplane's performance. It affects your climb rate, your cruise speed, your fuel consumption, and crucially, how far you can glide if your engine decides to take an unscheduled vacation. Understanding drag helps you manage your aircraft's energy wisely. It's like knowing how much gas is in your car's tank, and how to drive to get the best mileage. Now let's consider the glide part of our discussion. Imagine you're cruising along, enjoying the view, and suddenly the engine goes quiet. It's a scenario no pilot wants, but every pilot must be prepared for. In that moment, your airplane becomes a glider. How far can you travel without power? That depends immensely on how you manage your airspeed. Fly too fast and you'll come down quickly. Fly too slow, and you'll also descend rapidly, potentially even stall. There's a sweet spot, a specific airspeed that gives you the best possible glide distance. This magic number is your best glide speed, and knowing it by heart for your aircraft is absolutely non-negotiable. So why is this knowledge so critical from day one of your flight training? Because good habits and deep understanding are built from the ground up. Flying isn't just about manipulating the controls, it's about making informed decisions. Knowing about drag curves helps you understand why your airplane behaves differently at various speeds and altitudes. Knowing your best glide speed gives you options and time in an emergency. It transforms panic into procedure. This isn't just theory, folks, this is practical, hands-on knowledge that forms the bedrock of skillful airmanship. It's about being the master of your aircraft, not just a passenger with a license. Let's get into the details. So, what exactly is this drag curve we keep mentioning? Picture a graph. Along the bottom you have airspeed from slow to fast. Along the side you have the amount of drag. The drag curve is a line on this graph that shows how much total drag your airplane experiences at different airspeeds. It's not a straight line, it's usually shaped like a U or a smile. This curve is a fundamental fingerprint of your airplane's aerodynamic performance. Understanding its shape and what it tells you is like understanding your car's fuel efficiency at different speeds. It helps you operate your aircraft in the most efficient way possible, saving fuel and reducing wear and tear. Now, this total drag is made up of two main culprits. First, we have parasite drag. Think of parasite drag as all the resistance that doesn't help create lift. It's like dragging a big bulky suitcase through the airport. It includes form drag, which is caused by the shape of the airplane, the fuselage, the landing gear, anything sticking out into the wind. Then there's skin friction drag, which is the air rubbing against the surface of the airplane. Even a smooth surface has some friction. And finally, interference drag, which happens where different parts of the airplane meet, like where the wings join the fuselage, causing the airflow to get a bit messy and create extra resistance. Parasite drag gets much worse as you fly faster. Double your speed and you roughly quadruple your parasite drag. The second main type of drag is induced drag. This one is a bit trickier but super important. Induced drag is the unfortunate but unavoidable byproduct of creating lift. You can't have lift without it. Think of it this way. To create lift, your wings work to deflect air downwards. This process causes wingtip vortices, those swirling masses of air you might see on a damp day. These vortices mean that some of the wing's aerodynamic force is tilted slightly backward, and that backward component is induced drag. Here's the kicker: induced drag is highest at slow airspeeds when your wing is working at a high angle of attack to generate enough lift to keep you flying. As you speed up, your angle of attack decreases, and so does induced drag. So the total drag curve is the sum of these two troublemakers: parasite drag, which loves high speeds, and induced drag, which loves low speeds. At very low airspeeds, induced drag is dominant. As you speed up, induced drag decreases, but parasite drag starts to build up rapidly. The bottom of that U-shaped total drag curve, the lowest point, represents the airspeed where total drag is at its minimum. This specific airspeed is very important, as we'll see, because it's directly related to how efficiently your airplane can fly and glide. Understanding this balance is key to mastering your aircraft's performance in all phases of flight. Now that we've wrestled with the concept of drag, let's talk about a truly golden airspeed, the best glide speed. Often abbreviated as VG, this is the airspeed at which your aircraft will glide the farthest distance horizontally. For each foot it descends vertically with the engine inoperative. It's also known as the speed for LD max, which means the maximum lift-to-drag ratio. Remember that U-shaped total drag curve we talked about? The very bottom point of that curve, where total drag is at its minimum, corresponds to your best glide speed. Flying at this speed means you're getting the most bang for your buck in terms of glide distance. It's your airplane's most efficient state when it comes to covering ground without engine power. Why is this speed so incredibly important? Well, imagine the unthinkable happens. Your engine quits. Suddenly, you're a glider pilot. Your primary goal is to find a safe place to land, and to do that, you need to maximize the distance you can cover. Flying at your best glide speed stretches your glide path, giving you more options, more time to think, and a better chance of reaching a suitable landing spot. Deviate from this speed either by flying too fast or too slow, and your glide angle will steepen, meaning you'll cover less ground. In an emergency, every foot of glide distance counts. Knowing and immediately establishing this speed is a critical emergency procedure. So how do you find this magical best glide speed for the specific airplane you're flying? The first place to look is the Pilot's Operating Handbook, POH, or Airplane Flight Manual, AFM. Manufacturers determine this speed through flight testing and list it in the emergency procedures or performance sections. It's a number you should memorize like your own phone number. On the drag curve graph, it's the airspeed at the lowest point of the total drag curve. Some aircraft might also have it marked on the airspeed indicator with a specific color or line. It's crucial to remember that this speed is typically given for the aircraft at its maximum gross weight. If your aircraft is lighter, the actual best glide speed will be slightly lower. It's also important to understand that factors like aircraft weight and configuration, flaps, landing gear, can affect best glide speed. While the POH usually provides the speed for a clean configuration, flaps and gear up at max gross weight, any change will alter it. Lower weight generally means a slightly lower best glide speed. Extending flaps or landing gear will significantly increase drag and reduce your glide distance, and often the POH will state a different, slower best glide speed for such configurations, if gliding with them extended is even advisable. Practice gliding in a safe training environment with an instructor, of course, to get a feel for how your aircraft handles and to build muscle memory for establishing that crucial speed. Understanding drag curves and best glide speed isn't just academic. It has profound practical applications in everyday flying and, most importantly, in emergencies. Let's consider the most critical scenario, an engine failure after takeoff or during cruise. The moment that engine goes silent, your training needs to kick in. One of your immediate actions, after pitching for best glide speed, is to use that speed to maximize your chances of reaching a safe landing area. Knowing VG allows you to accurately judge if a potential field is within reach. Without this knowledge, you might try to stretch a glide to a field that's too far, or undershoot one that was perfectly attainable, simply by flying at the wrong airspeed. Beyond emergencies, understanding these concepts makes you a more efficient pilot. For instance, if you need to maximize your aircraft's range during a long cross-country flight, perhaps you're facing unexpected headwinds or trying to conserve fuel, you'd want to fly at an airspeed that gives you good efficiency. While best glide speed is for engine-out situations, the speed for maximum range is closely related to the point of minimum drag. Flying near this speed, often slightly faster than best glide, helps you cover the most nautical miles per gallon of fuel. This is because you're operating where the engine and airframe are working together most harmoniously against drag. It's about being smart with your resources. Think about other phases of flight too. When you're trying to achieve the best rate of climb, VI, you're fighting against drag. While VI and VG are different speeds, the underlying principles of managing drag are similar. When you're descending, controlling your airspeed based on drag considerations can help you plan a smooth arrival or manage energy effectively if asked by air traffic control to expedite your descent or slow down. For example, if you need to lose altitude without gaining excessive speed, you might deploy flaps or reduce power. Understanding how these actions affect the drag curve and your descent profile. It's all interconnected, making you a more proactive and knowledgeable pilot. In conclusion, mastering drag curves and best glide speed is fundamental to safe and efficient flying. It's about understanding the forces acting on your airplane and using that knowledge to your advantage. Always know your aircraft's VG by heart. Practice establishing and maintaining it during your training. Refer to your POH regularly. Remember that parasite drag increases with speed, while induced drag decreases. The total drag curve shows you the sweet spot. These aren't just numbers or graphs. They are tools that empower you to make critical decisions, especially when it matters most. Fly smart, fly safe, and always keep learning. That's the mark of a true aviator.